name is Emily King. I'm a rising junior here at the University of Michigan. I am a Consortium for Verification Technology undergraduate fellow, part of the Detection for Nuclear Nonproliferation group. In this presentation, I will discuss my current research project, which focuses on eliminating unwanted data from data sets that are used for nuclear material detection. Organic liquid scintillators like these can be used to detect various particles that interact with them. The particles come off of a radioactive source and go into the scintillator and interact with the liquid inside, which produces light. The light is then amplified by the photomultiplier tube and turned into digital pulses by the digitizer, which can then be analyzed for information. Pulse shape discrimination, more specifically charge integration, requires integrals of the total and tail of the pulse to differentiate between neutron and photon particles. Each nuclear material has a specific signature of the particles it gives off, so we can use this pulse shape discrimination to determine the type of radioactive material we're detecting. This is especially useful for detecting special nuclear materials like plutonium that can be used for illicit and dangerous purposes. If two pulses come in the same time window, we call it a double pulse. Double pulses are bad for our analysis because the extra space under them makes it impossible to compare to a regular pulse. Therefore, we just want to dispose of these double pulses before we start our analysis. Here's a picture of my experiment. I varied the distance of the source to the detector so that I could get a different count rates. I wanted the different count rates because then I would have different double pulse probabilities. I did this so I could test my method of eliminating double pulses with data that has varying amounts of double pulses. My method uses a script in Python that takes the second half of the pulse and applies an exponential fit to it. It does this to a subset of data, which I can take and plot the decay constants that were found as a function of the pulse's height. This allows me to make computing 8 times faster by using this decay constant function to find all the decay constants for the full set of data. I call the exponential function that's produced the template. After creating the template, the script takes the root mean square error between the template and the pulse. A double pulse is going to have a large discrepancy between itself and the template, so we can apply a threshold, which we use to differentiate between double pulses and regular pulses. After using my data to test how many double pulses were disposed of and comparing those results to a current method in place and the theoretical amount of double pulses that should be present, my results show that the current method and my template method are about the same when looking at all pulses. But when you look at only low energy pulses, template method is far superior. This is useful because pulse shape discrimination gets difficult at low energies due to overlap of neutrons and gammas. Disposing of the right amount of double pulses widens this gap, making PSD easier and more accurate.